Great. So, our first talk today will be statistical learning with a nuisance component, also known as orthogonal statistical learning. The talk will be given by Vasilis Syrgkanis, who is a principal researcher at Microsoft Research New England, even though right now he is in Greece. So this paper got the Best Paper Award at COLT last year, and it was co-authored with Dylan Foster. Let me remind you that this will be a talk of 25 minutes, followed by 4 minutes of questions and answers. Please enter your questions in the chat box in the Zoom client. So thanks, everyone. And Vasilis, if you want to start.
Great. Thanks, Flavio. Thanks for the introduction. And thank you all for inviting me to speak about this paper. So this is importantly a joint work with Dylan, who is currently at MIT. The main motivation of this work is coming from this area of causal inference in machine learning. In the last few years, we've seen machine learning infiltrating decision-making in a multitude of application domains, from business, personalized medicine, and law. There are many instances where machine learning has been used to answer questions that are related to decision-making, such as who should we offer a price discount? Who should we treat with cancer immunotherapy as opposed to more traditional therapy? What bail should the judge set for a particular defendant? However, there is a small discrepancy between decision-making questions and what machine learning has traditionally been founded on, which is this area of statistical learning theory. And in particular, when I talk about machine learning in the context of this talk, I'll be mostly talking about supervised learning, which a bare bones description of the area is a set of algorithmic and statistical tools for solving the following problem. Given training data, which comprise of features and an outcome drawn from some distribution, try to find a model theta that is a mapping from the features to the outcome that has a small expected prediction error on new samples drawn from the same distribution as the training samples. More generally, this is an instance of the general field of statistical learning theory, where you're given training data drawn from some distribution and you have some population loss in mind, and your goal is to find a model based on the data that has a small excess risk, so that it minimizes this hypothetical population loss, only having access to finite sample data. The problem is that in the context of decision-making, the statistical learning theory framework is not really very well suited, at least at the first sight.
Can I stop you for 1 second? We only see the title slide. I don't know if you switch to some other slide, but we only see the first slide, at least Mozen and myself. That's what we see.
Okay. Let me see. Is it better now?
No, yeah, now I see another slide. Yeah.
And you're using the slides? Yeah, so this was just a slide with the decision making. Anyway, so in the context of decision making, if you try to understand what the vanilla version of a statistical learning theory problem is doing, is basically trying to address a question of the following form. If you were to continue to follow the same decision policy as the one that you were using when you were collecting the training data, then can you predict the expected outcome given a treatment or an action and a set of features? On the other hand, most decision-making questions are primarily targeting questions where you want to understand what will happen if you change the policy than the one that you were using in the training data. So what would have happened had you treated this particular person with a different treatment or chosen a different action? And so essentially, most of the causal questions are questions where the distribution on which you want to test your model on is very different from the distribution of the training data. And deep down, this is also a difference between correlation versus causation. the vanilla statistical learning theory framework is particularly well suited for addressing correlation questions, trying to find complex correlation patterns in your data. While most of decision making is trying to understand causal relationships, which variable causes a change in the outcome, or how much change does this variable cause to your outcome. And so when you're trying to blend causal inference and machine learning, one question that you might want to ask is there a way to express causal estimation as an excess risk or a statistical learning theory problem? And a sneak peek into the main framework and the main results is that typically you can formulate several causal inference questions as a statistical learning theory problem. But most of the times when you try to do that, the loss function that you will be interested in will need to depend on auxiliary models that you don't know and that you also need to estimate from the data. These auxiliary models, essentially what they're trying to do is capture other correlation structures in the training data that can be used to address this distribution shift aspect of the causal question. So to be even more concrete, let me go through a particular example that will be a small instance of the framework that we presented in this work. And this is an example of estimating price elasticity of demand. So suppose that you're a data scientist and that someone gave you a data set from prices and demand from last year and asked you to understand how does demand for a product change as a function of price. And suppose that these were the data points in your data set. You only had 6 data points for simplicity. And this is how they looked at if you plotted them, where on the x-axis is the price and on the y-axis is the demand. Typically, you take the log of the price and the log of the demand in demand estimation. And then you try to fit it into a statistical learning theory framework. Say you try to find a curve that predicts the demand from the price as a function of the price. And in this case, even a linear curve would have a very good fit. And this would be the best fit. It has a small mean squared error. And you might even say that this has a very good fit on your data. And so then you would be tempted to conclude that this is the effect of how the demand changes as a function of price. And then we would go back to the business decision maker and say, okay, we should increase our price to infinity because as we increase price, demand also seems to be increasing. So this is obviously a blatant mistake. And the main problem that arises here and that you typically get in observational data is that there are several other variables that simultaneously correlate with the treatment that you want to make an intervention on and with the outcome that you're interested in. These variables are typically called confounders. For example, it might be that price changes during winter because in anticipation of demand, because we expect that demand is also going to increase during winter. And so it's not that price really causes the increase in demand, but it's just that there's this other variable that simultaneously increases demand and price. One way to address this problem is to try to fit a bigger model. Let's try to incorporate the season indicator into our prediction problem, into our machine learning problem, and try to fit this bigger model where we have this extra variable. This will actually, in this particular example, will solve the problem. Now, say the lower points were all coming from the winter season, from the summer season, and the higher points were all coming from the winter season. And then locally within those clusters of points, you would be fitting a downward sloping curve. And so the coefficient that you would be fitting in front of the treatment is going to be a negative one. And you're going to be estimating correctly that increasing price decreases demand. However, you're going to be certain that, that you estimated a causal effect and that this is really going to be the effect of price on demand. You typically need to control for many such potential confounding variables. And in applications, it might be hundreds or thousands, especially if you want to control for complicated ways that the confounding variables will have an effect on the outcome. For instance, you might want to control for the time of day, for the day of the week, for the month. browsing history if you're in an online application. And so typically you will need to estimate a very complicated and complex machine learning model with hundreds or thousands of variables, where you only care about this small coefficient, this the scalar coefficient in front of the treatment. And so you're sort of like causal, you manage to reduce your problem to a prediction problem, but now this is a much harder sort of statistical estimation task than fitting a one-dimensional sort of linear regression. And many times the estimation rate that you will be able to achieve for this confounding effect, for this function f naught here, will be much slower than a parametric estimation rate. For example, a rate of 1/√n when you have n samples. And so one main question is, can you still solve this problem even if the confounding effect is so complicated and you cannot get 1/√n rates? Is there any way to estimate this causal effect in a way that your estimation error on the effect is robust to the estimation error of these auxiliary models that you don't really care about? You don't care about how all of these confounding variables affect the outcome, but you have to estimate in order to be able to interpret your coefficient in front of your treatment as a causal coefficient. And so here's one way that you can achieve that. And let me start with a reinterpretation of what the causal effect is, how you can think of the causal effect, and then go to a concrete estimation algorithm that will have this robustness property. One way to think of the causal effect is the following. First, you can try to estimate the two important quantities, which is the residual treatment and the residual outcome. The residual treatment is what is the variation in the treatment that is unexplained by all of these confounding variables. This is basically the difference between the treatment that you observe, the price, say in the pricing example, and the output of a prediction problem that tries to predict the treatment as a function of the confounding variables. So this is this quantity over here, expected treatment conditional on X. And so this residual is essentially the unconfounded, the independent variation in the treatment. You can think of this as some form of random experiment, some change in the price that you can treat it as a randomized experiment. And then the other quantity is the residual outcome, which is the variation in the outcome that is unexplained by all of these other variables. And again, this is the difference between the outcome and the output of another prediction problem, where you try to predict the outcome from these confounding variables. Then the interesting observation is that the causal effect can be thought as exactly the correlation between this residual outcome and this residual treatment. So it's the correlation of these unexplained variations in the outcome and the treatment. And so you can think of this as a single-dimensional linear regression where you're trying to regress the unexplained variation in the outcome from the unexplained variation in the treatment. And the intuition is now that you've reduced it to a single-dimensional problem, hopefully you will be getting rates that depend only on this single-dimensional, statistical problem, and will not get a very heavy impact from the fact that you hadn't really solved you didn't really know these conditional expectations, but you estimated them in a first stage. And this is exactly the estimation algorithm. This is exactly what the estimation algorithm that corresponds to this rethinking of the causal effect manages to do. And so here is an estimation algorithm that was proposed recently by in the econometrics community, where what you do is the following: you split your data in half, and on the first half you train an arbitrary machine learning model that tries to predict these two conditional expectations. So the first model tries to fit the conditional expectation of the outcome conditional on the confounding variables, and the second, the conditional expectation of the treatment conditional on the confounding variables. And then given these two models that you fitted on the first half, you go to the second half and you calculate these unexplained variations and you run a single-dimensional linear regression between this between the unexplained variations. The nice property of this estimation algorithm is the following: assuming that your first stage estimates satisfy a minimal requirement that their mean squared error is small, but still a slow decay. So not parametric, but 1/n to the 1/4. So slower than 1/√10. So they can be quite poor estimates. As long as both of them are of the order of 1/n to the 1/4, then the final estimate theta hat is root-n consistent. So its mean squared error decays as its root mean squared error decays as 1/√n. So it achieves a parametric rate. And the other important part that a lot of econometricians really care about is that the distribution of this estimate is going to be asymptotically normal. So you can also construct confidence intervals around this final estimate, as if you had no estimation error coming from the first stage. And the key intuition behind this result in econometrics is that this estimator, this final estimator that runs a linear regression of the residual on residual can be thought as a solution to a moment equation that satisfies a property known as Niemann orthogonality that dates back to early work of Neyman in the 20s on hypothesis testing. I'm going to go into more details on the technical details on this notion of Niemann orthogonality a bit later on when I present our framework and our results. One extra observation about this theorem is that even though it's a very nice theorem about estimating an average effect, many times when we do, in many of the recent applications of causal inference, we don't just want an average effect, but we really care about how this effect varies with observable characteristics, primarily because we want to deploy personalized policies. We don't just want to either treat or not treat everyone, but we want to understand who should we treat and what action should we take conditional on observable characteristics. So for this, we don't just need to estimate a constant in front of the treatment, but how this constant varies with observable characteristics. So we're more interested in estimating a function that maps the observable characteristics x into a causal effect. And this is known either as the heterogeneous treatment effect or as the conditional average treatment effect. Now, there is an easy adaptation of the previous estimation algorithm that addresses this more complicated problem, essentially reducing it again to a machine learning or statistical learning theory problem. Instead of just running a linear regression in the final stage, we're going to solve a much more complicated statistical learning theory problem where instead of minimizing over a scalar, we're just going to minimize over effect functions that come from some hypothesis space theta, this residual on residual linear regression where now the coefficient in this linear regression can be heterogeneous and can depend arbitrarily and flexibly on these observable characteristics. And there has been several lines of work that try to analyze this particular estimation algorithm for different hypothesis spaces. For instance, Nye and Wager analyzed this algorithm when the final estimation algorithm is a kernel ridge regression. Or in a work that we did with Chernozukov et al. And a prior work, they analyzed results when this final stage was solved via the lasso. Or in another work that we did, we analyzed this algorithm when the final stage was a random forest. More generally, you can think of a meta version of this algorithm where you don't just choose a particular estimation algorithm to solve this final statistical learning problem, but you can use any machine learning algorithm that has small plug-in excess risk, which is what really statistical learning theory is all about, finding a model that has small excess risk for a given loss function. And now the loss function is the loss function where you plug in the estimates from the first stages, but not the true nuisance models that you don't really know. And so here this population loss function is this residual on residual, and you can use any algorithm that has small excess risk with respect to this plug-in residual on residual. And then there's a theorem, a meta theorem that you can show that assuming that the first stage estimation has small root mean squared error, say epsilon n, then and subject to a condition that there is unexplained variation almost everywhere. So for every x, there is some unexplained variation in the treatment, so there is some randomization. Then you can show that the final estimate, the final causal model of the heterogeneous effect is going to satisfy a mean squared error guarantee that gets a small impact from the estimation error of the first stages. So here we get that the error of the first stages appears with a square. So if in the parametric example, if kappa n was 1 over root n and epsilon n was 1 over n to the 1/4, then this second term over here would be of a lower order and would be sort of asymptotically negligible. And so this is an example of there were several such papers showing results like that in the literature for particular estimation algorithms, as I was saying before. And in this work, we were essentially trying to prove a meta theorem that generalizes all of these particular algorithms and prove something for any machine learning algorithm that has a generalization error. And an instance of it is this generalization guarantee that I presented in this slide. But this is also a small instance of a more general result, which we propose in this work, and which also captures not only the heterogeneous treatment effect estimation, but several other applications that come up in causal inference and in policy learning, and in several other applications in statistical learning theory. So what is this general framework? So it's the framework of a statistical learning with a nuisance component. So suppose that you manage to show that the model that you really care about can be phrased as the minimizer of a loss function, which, however, depends on auxiliary nuisance models that you don't really know, and you also need to estimate from the data. So in this example, these auxiliary nuisance models were these first stage prediction problems for predicting the outcome from the confounders and predicting the treatment from the confounders. And what you care about is, given n samples, find a model theta hat that has a small oracle excess risk. So even though you don't know these nuisance models, you care about an excess risk bound on the loss function at the true nuisance models, not at the estimated ones. The reason why we make oracle excess risk as our primary goal is that it is an umbrella, it is what sort of like statistical learning theory typically cares about. So it matches the statistical learning theory paradigm. And also, in many applications, it takes a very meaningful problem-specific interpretation. For instance, if your loss function is the square loss, it looks like a square loss, then typically you can show that an oracle excess risk bound will imply a mean squared error of your model theta hat. In other applications, like in policy learning, where you're not trying to estimate a heterogeneous effect, but rather estimate directly a model that tries to predict what treatment to give at a particular X, then this oracle excess risk bound takes the interpretation of the regret of the estimated policy theta hat. So then we wanted to analyze a meta algorithm where we split the data in half, and in the first stage we estimate, using whatever estimation algorithm you want, a model G hat of the true nuisance models that satisfies some norm guarantee, some consistency rate, epsilon n. And then in the second stage, you use an arbitrary machine learning algorithm or a statistical learning theory algorithm to get a model theta hat from data that has a small plug-in excess risk. Now, because here we are asking for the algorithm to have a small plug-in excess risk, this is now a more standard statistical learning theory problem, because now we know what the loss function is. There's no unknown component. We're plugging in the model that comes from the first stage, and we're asking a small excess risk for this instantiation of the nuisance model and not for a hypothetical unknown nuisance model. So this is something that most of the techniques in statistical learning theory and machine learning can handle. And so there are many algorithms that will give you small plug-in excess risk. And now the main question is, when is the oracle excess risk at the true nuisance components, which could be far away from the estimated ones, robust to estimation errors in these first stage nuisance models? And here comes this idea of Niemann orthogonality from econometrics, and we propose a generalization of Niemann orthogonality for loss functions that seems to be, that is the sort of like a crucial property that implies robustness of the means of these first stage errors. So what is Niemann orthogonality? First, I need to define what the directional derivative is. For any functional direction nu, the directional derivative is basically the derivative with respect to taking a small step in that direction. And then what a Niemann orthogonal loss is a loss function whose cross functional derivative, when I first take a derivative with respect to theta, and then I take a derivative with respect to the nuisance model, is equal to 0. The intuition, and this is evaluated at the true and the oracle nuisance functions, and the intuition is that small perturbations in the nuisance model G around its true value do not change the gradient information a lot, the gradient information of the loss with respect to the target function. And so if something was a first order local optimum of the oracle nuisance function, of the oracle loss function, then it will also be a first order local optimum if I slightly, close to first order local optimum, if I slightly perturb the nuisance by a bit. For example, in the pricing application, if you take first the derivative with respect to the target model, you're going to get this linear in Q and P quantity multiplied by T minus P. And then if you take the derivative with respect to the nuisance, say for instance Q is the nuisance, you're going to just get this T minus P naught arising here. And because the expected T conditional on X is equal to P naught, this is going to be a mean zero quantity. And so this loss function of the residual that we presented in the pricing application satisfies this Niemann orthogonality property. And so the main theorem that we have is that if the loss is Niemann orthogonal and strongly convex in theta and smooth, then the oracle excess risk has a second order effect from the first stage estimation rates. And these are standard technical definitions that I'm gonna skip over. And then we have also another theorem that says that that does not require strong convexity, which is a strong assumption. In the absence of strong convexity, then we also get a second order effect, but the second order effect is to the square. And this difference comes from the fact that when you have a strongly convex function, you should expect fast rates of the order of 1/n for parametric problems, while when you don't have strong convexity, you should expect slow rates. And this also appears in the second order term here. However, without strong convexity, we need a slightly stronger Niemann orthogonality property that holds for all models theta and not just at the true model theta.
Vasilis, your time is almost up, so
in the paper we present several other results, such as how you construct such orthogonal losses from non-orthogonal ones, how do you derive tighter bounds for particular estimation algorithms, or when is the rates that you get minimax optimal for the function class that you're interested in, and several applications of this approach for different problems in causal inference. So some main takeaway points: causal estimation can many times be reduced to generalization or excess risk bound problem, albeit many times this the loss function that you're going to get is going to depend on nuisance models. Niemann orthogonality, which is an idea from semi-parametric statistics and econometrics, can improve machine learning theory for such causal problems and lead to robustness to nuisance errors. And focusing on excess risk in causal problems can lead to more robust theorems in causal inference with fewer assumptions, and enables the use of recent advances in statistical learning theory. And if you're interested, we also have an open source package that implements several of these methodologies, and you can just try it out. Thank you very much.
Thanks very much, Vasilis, for the very nice talk. And I guess we have 1 or 2 minutes for questions. If people connected to this Zoom want to write down their questions in the chat, then I will be happy to read them. We don't have much time, so it would be great if these questions come right away, or thanks. Okay, I guess we have to move to the next speaker.